B11 is about conservation of momentum and energy. And our first question, we're asked to state Newton's third law. Well, stating Newton's third law includes that forces come in pairs. And by this we mean for every force acting on a system, there is an equal and opposite force acting on the system. So if we can't seem to detect the second force in the pair, that means we haven't properly defined the system. But that's Newton's third law. Now, the law of conservation of momentum states that the total momentum of a system remains constant unless acted upon by a force external to the system, as in an exploding body or two or more colliding bodies. We could probably just leave it at two, or just colliding bodies. In this particular case, we really need to add this last part to earn the second point that's described. So now we are given these two balls. We have velocity A and B. B is at rest, so V0 equals 0. And it's moving along a line that passes through their centers. So that's the direction of velocity. They each have a mass m. So this has mass m and this has mass m. So they have the same mass. A magnitude of the force that A exerts on B is Fa. So A is going to exert a force like this called Fa on B. And B then is going to exert a force on A, that is force of B on A. So we're now asked to draw those forces and label them to represent the magnitude and direction of the forces. So we could start here at the center and say FAB, and over here we could start at the center and say FBA. And we could draw those equal lines, and we can say equal and opposite. To be more precise, we could say equal in magnitude and opposite in direction. So those are our forces acting on those balls. A exerts a force on B and B exerts a force on A. No matter what happens afterward, that's an action-reaction pair. So now we're told they're in contact for time delta t, and that means the time that A is in contact with B is delta t, and the time that B is in contact with A is delta t. The speed of A is VA and the speed of B is VB. There's a change in momentum of A and a change in momentum of B. It doesn't say there's a change in the total momentum. It's just saying each of their individual momenta change. So now we're asked to use Newton's second law to deduce an expression relating the forces to the change in momentum. So on B, so the Newton's second law is that the net force is equal to the rate of change of momentum. And the momentum in this case is a result of m times the change in velocity over the change in time. Now, the change in velocity of B is actually VB. It goes to delta V for B is the final VB minus 0. It was stationary. So delta VB is VB. So the net force in this case, FA on B, that's the net force causing this, is M VB over delta T. And we can rearrange that because it wants forces to the change in momentum. We can rearrange that to be FAB delta T equals MVB. So this is the delta P, and this is the forces expression. In ball A, we have an F net is delta P over delta T. And of course, that is M delta V over delta T. And this is the force of B on A. And the mass is the same mass. But when we look at delta V here, delta VA, the final is VA minus V, which is the initial velocity. So we have M VA minus V all over delta T. And then rearranging this, we can say FBA delta T equals M quantity VA minus V.